Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. Okay, so in this video we're going to try model something called a ribbed reinforced concrete slab, in which we are going to take a look how to model those things and maybe take a look on the design of those things either in this video or in the later video, depending on how long it takes us to model those things. Now, first things first, I'm kind of out of my usual recording spots, so you might hear differences in the voice or sometimes even like the voice of the surroundings of me, but I hope this will not basically affect you. Alright, so with that being said, we need to understand what is a ribbed slab. Now, ribbed slabs are reinforced concrete slabs that do not concrete the entire volume of the slab, rather have some voids by some placeholders that will cause concrete to flow in ribs, and that's why it's called ribbed slab. Now, this is basically an unfinished bottom surface of a slab. Of course, they do look like this sometimes. In this case, the placeholders are removed, but in some cases, the placeholders will remain. I mean, here the placeholders are removed, and they are usually put like this before casting, and then they are cast, the concrete is cast, and the placeholder is removed. And the end result would look something like this. Now, sometimes placeholders are set to be permanent, like those blockworks. If you put blockwork in reinforced concrete slabs, then usually those blockwork pieces will remain in the slab and will not be removed, basically. You can see the multiple pictures here. Just Google ribbed slab and you will see all kinds of slabs with blockwork being permanent in those slabs. Ribbed slabs come into two possibilities. They are one-way ribbed slabs, in which case the ribs move in one way. And there are two-way ribbed slab, in which case the ribs move in two ways. And we're going to try model both. All right, so to continue, well, this is, well, a one-way ribbed slab. Of course, the drawing here is for illustration purposes only, and this is how it looks like in real life with all kinds of blockworks. Those pipes, now those are infrastructure in the slab. I think those are electrical infrastructure, but sometimes they also have bigger pipes, which are the sanitary infrastructure inside the slab. Now, the reinforcement of such ribbed slabs basically are a steel mesh on the top slab, or the topping slab as we call it, calculated based on minimum reinforcing steel or 5/8 each 150 millimeters and so on. And the ribs concrete that are between those blocks are usually designed as little beams with no shear reinforcement, and those ribs usually have two reinforcing bars passing through them as little beams. The shear strength of those ribs is allowed to be used as concrete, and I think the SI code has a provision for that where it allows 5VC to be multiplied by 1.1 to be increased for ribbed slabs only. But I will have to look this up again before I say this with 100% certainty. Anyway, how do we model those things? Now, those things are beams, and to model them, we need to understand how those beams look like in the structure. So to understand this, here is a little drawing for you. Now, a ribbed slab from top looks kind of like this, where you have those little rib or those little block lines aligned like this, and you have in between those rib blocks, in between those block lines, you have the concrete thing, which is basically those things. If you just take a cross section like this and draw the section here, you understand that you have multiple ribs. This is rib number 1, this is rib number 2. To explain that, here is a little like painting of that. This is like the rib I'm talking about. And if you take the cross section of the rib, because you're going to model it as a beam, then you need to understand, of course, what those cross section dimensions are. Now, the lower width is the width of the web, and this is usually the spacing between the blocks, and sometimes it's taken between 100 millimeter and 150 millimeter. I'll take it as 120 millimeters. And what about the upper flange width, B flange? This is the center to center spacing of blocks. Now, it is basically the block width plus the 120 millimeter in bottom here. Now, the block width of the ribbed slab depends on the local practices at your country. Now, at least from where I was working, the ribbed slab blockwork has a dimension of 400 millimeters multiplied by 400 millimeters multiplied by a variable height. So basically, the plan of that thing is 400 millimeter in the width and 200 millimeter in the length, if you want to call this length, and the height of the block is variable. So here in this case, the spacing would be, assuming the 400 millimeter thing, the spacing would be 520 millimeters center to center which is basically the width of the upper flange. Of course, there is the final rib, which is on the edge, but it doesn't count. What I'm talking about is I'm talking about this thing, the final rib on the edge, but it doesn't count because usually the final rib doesn't exist. The final rib is replaced by a little beam, which is 20 millimeters of width and is being stirrupped. So usually we do not have a final rib in the last line. We have a beam that carries that thing. All right, so with that being said, let's continue about our work. And we need to know, of course, the height of that struct of that section. Now, the total height of the rib here is basically the height of your slab. Of course, you will choose a thickness of a slab, and the thickness of the slab is going to be the height of your rib beam. And let's say that the thickness of the slab is 250 millimeters, just saying. Of course, it depends on the flexion calculations. It depends on so and so. And of course, there are some provisions in the ASI code that try to give you an approximate height for those ribbed slabs. I will assume it to be 250. You might have seen ribbed slabs that are up to 300 millimeters. That also happens. And the good thing, I'll talk about advantages later, but the good thing about ribbed slab is that they reduce weight, so you can actually go to 300 millimeters with a straight face, and even 400 sometimes, but of course 400 is too much. You can go to 300, 320 millimeters with a straight face because you're reducing the weight via those ribs here. I'll talk about the different weight reduction schemes in ribbed slab later, but for now, I'll continue my explanation. All right, so the last thing that remains is, of course, the topping slab, which is this thing. The topping slab usually is chosen so that it's enough to resist the cracking strength here. And for a 400 millimeter rib, it is found that at least 80 millimeter, if not 100 millimeter, is good enough. So you can choose it between 80 millimeter to 100 millimeter to be in the safe side. Now, this topping slab, basically this, which is this thing, it is part of the ribbed beam, yes, but it also contains a steel mesh that is just laid in both directions, in this direction and in the perpendicular direction, but I'm running out of space. This steel is calculated based on the minimum steel of a slab that has a height of 100 millimeter or 80 millimeters, so you can calculate this via your code. This steel mesh is not part of what I want to design because this is just minimum steel. What I want to design and model is the rib itself. This is just called a topping slab, and I'll have a little hack to model it later. What you see here is a one-way ribbed slab with the force being transferred in the vertical direction. Of course, there are two-way ribbed slabs too, so let's take a look on those. Now, to make a two-way ribbed slab, you have to be a little bit creative in your block arrangement. Now, a two-way ribbed slab means that your block work is not going to be on stripes like this. It's going to be 2 blocks and then an empty space, and 2 blocks and then an empty space, and 2 blocks and then empty space, and so on. This is how you would do a two-way ribbed slab. I'm saying 2 blocks, but it's not necessarily 2 blocks. You have seen other pictures where the ready-made plastic rib is already accounting for that distance. But I'm talking about the practice of placing blocks inside the slab and not placing ready-made plastic things. If you have ready-made plastic things, you just put those things and good is. But well, you do not have that in my case, so I'm just going to use block work here. So I would put 2 blocks, and you see this is like a little two-way thing, as you can see, 2 blocks. But of course you do this on the entire panel. So it kind of looks like this. Now, what are the dimensions that you see here? Well, the dimensions that you see here are the following. If you put 2 blocks which have 200 by 400 millimeter dimensions in the plan, then you would have a cell of blocks that is 400 by 400 millimeter, which is basically a perfect square in this case. And the good thing about this is that you could have almost identical ribs in both directions. You would have ribs like this. If you cut them, you see the same thing here. And if you cut this way, you would see the same thing here. That's kind of cool. So, of course, that's one possibility. You could have unsymmetric ribs, and if you have unsymmetric ribs, then, well, you have to design both ways. One final thing I didn't touch on is the height of blocks. Now, this is highly regional dependent. Like, what kind of rib block would you put here? Of course, you would put a rib block that allows you to have 80 to 100 millimeter topping slab. So if it's 250 here, depends of course on your region. Like for example, if you have 180 millimeter height blocks, you cannot put that because it would have 70 millimeters topping slab, which is in my opinion kind of low. So you would choose, for example, 150 millimeter height of blocks, which will allow you to have a topping slab of 100 millimeters. Of course, this is something you should decide, but I'm just here to give you a little introduction to ribbed slab design. Now, of course, if you know this already, then of course you're face palming now and thinking, oh my God, what do I need of this? But I hope that at least some information might be conveyed here. And we'll take a look on this in robots in a moment. Before I finish, why do we use ribbed slabs? Well, it's obvious from the pictures that you can achieve higher thickness concrete slabs that are not as heavy as solid slabs because you are replacing part of the concrete which has a density of 25 kilonewton per meter cube. You are replacing it with blocks which are usually hollow in the inside, which will cause your weight to drop down. And sometimes you're not even replacing the concrete, but you're actually removing it entirely, as in here. When you put plastic things like this and you cast your concrete, then you are going to remove the plastic ribs and the entire concrete gets replaced by air. This causes some weight reduction. You can actually make slabs span longer distances by not basically increasing the material cost. But of course, one important thing I want to mention here is to take a look on the concrete near the column. You can see that the concrete near the column is intentionally not ribbed. And of course, we have seen this. The reason behind that is, of course, the punching shear on concrete columns that will occur near the columns. That's the reason why they make it as solid. Now let's go back to modeling that thing. So I'll assume that my slab is a trapezoid, which is 0 in X, 5 in X, 10 in X, and in Y it's going to be 0, 5, and 3.5 because I want to have a trapezoid. I hit the apply button, click OK. So I go to view. Of course, the story height I don't care about today because I'm not designing columns here. I'm just modeling the ribbed slab. Look, I mean, those ribbed slabs, those ribs, where are they going to put their load on? The ribs are not connected to each column, you know, so the ribs are usually connected to a reinforced concrete beam that carries the load into a nearby column. So in the end, around the ribbed slab, you would have a reinforced concrete beam that would carry the load to the nearest column, basically, if you have those beams. And you would have like 6 columns here. For example, here you have a column here, here, and so on. Then you can see the load path, basically. The load path here is, well, the human stands on the slab. The slab carries the load by the web or the ribs, and the ribs transfer the load to the beams. The beams transfer the loads to the columns, and of course the columns keep transferring the load vertically downward until we reach the foundation. This is called the load path. Now going on with this, I'm going to model my structure. So I'll choose a reinforced concrete column. I see beams here because I misclicked. So I click on reinforced concrete column, select my column. Of course, I'm selecting placeholder columns now. I don't really care about them at the moment. So I'll just select the cross section here. And well, I'm just going to put me the columns here. Now let's put some beams. Well, I'm going to put me a reinforced concrete beam here. And let's go to a beam here. Let's select as reinforced concrete beam. I'm going to assume me a beam of, I don't know, like, now wait, I made a concrete column like this. So my beam should be less than 400 millimeter in width to be able to connect with the column. I'll choose a beam width of 250 with a height of 400 millimeters. This is a drop beam. There is something called hidden beams, which are beams that are not thicker than the slab. And of course, this is well known around the world. The problem with drop beams, as I'm doing them right now, is that they need finishing, architectural finishing, so that they are not visible for the human eye when they basically live in the structure. Because if I put a slab now on the drop beam, then the person will see the drop beams would look like not look really nice. So usually you would have architectural finishing below the drop beam to cover and hide the drop beam. Now recently, with the advancement in gypsum board manufacturing, I think a lot of people are considering gypsum to be their finishing in their structures. Previously, like years ago, gyps was basically cast in molds. You need a higher skilled professionals to do gyps works for you. But now with like the accessible gypsum boards and the switch of labor into using those gypsum boards, I think that we are getting better and better at that. Anyway, now let's get to the meat of the thing. I'm going to make me a rib, and to do that rib, I will just select me here a reinforced concrete beam. I'll go to this, and I'll ask him to make me a T-section. The dimension of the T-sections are: the B here is 120 millimeters, the flange is 520 millimeters, as we have explained before. The height of the flange is 100 millimeter, and the height of the entire thing is 250 millimeter. Now you could reduce the moment of inertia here to account for ACI code requirements, but I want it to be code neutral, so I will not do that. Please refer to your own code, checking out if you need to reduce moment of inertia or not. And I argue here that this is not a beam, but this is a slab. So when you reduce the moment of inertia of a rib is part of a slab system, so you should be using the coefficient of reduction of the ACI code for slabs. I'm saying ACI code, but of course you could have different codes, so please, I'm trying to be code neutral, so I will not reduce the moment of inertia, but I'm hinting at it so that any user who's listening to me now knows that he needs to reduce the moment of inertia. All right, so now I have my section, I guess. I'll add that, and I'll close, and I'm gonna start putting my first ribs. Now to do the first rib, you need to have the first distance here. So in this structure, I'm gonna do one slab that is one-way and one slab that is two-way. And I want to explain some cool ideas about the one-way, two-way systems. So now I will have one-way slab, which will basically my ribs being going to this way, so they are moving in this direction, in the X direction. So I need, of course, a starter point to start with. Now I'm gonna select this beam. I'll go to edit, move or copy, and I'm gonna copy it the distance of a rib. Here is my beam. The beam had a dimension of 250, and I want to connect a rib to it. And the question is, what's the center spacing of the first rib? Because this is like one of the issues you need to take care of. Now, to be honest, if you mess up the first spacing, it will not be like a big difference, but why not be accurate? So the first spacing is going to be basically 250 plus 520, all of that divided by 2, between two brackets here. So this plus this in brackets divided by 2. So let's calculate that very quickly. I open my calculator. 250 plus 520 divided by 2 is 385. Okay, so the first rib seems to be spaced 385 millimeters. So in X I have no spacing. In Y I have 0.385. In Z I have no spacing. I'll execute this, hoping it works. It seems to be working, but of course the final test is when I put a rib section on it. So let's put the rib section on it. Let's take a look if it works. And this should be, it's not perfect. Is it perfect? Okay, it is perfect. Let me just check very quickly. Right. Yeah, it's perfect. It's aligning perfectly, so we are right. But of course I need to continue my other ribs. Don't be discouraged of this little step you see here. This is finite element stuff. The finite elements need to be connected in the center. So this step is necessarily for graphical interpretation. You don't need to offset that thing, because offsetting will cause the axial forces to cause moments, which is, of course, in our case here, inadequate. I'll take my rib here, go to edit, move or copy, and copy it multiple times off a spacing off, and this time the spacing changes, 0.520. And I'll make me, I don't know, I'll make me like 10 repetitions, and then I will delete the rest. I'll execute this. I have my ribs. Now I don't need some of them, so let me delete them very quickly. This is overshooting, so no need for that. Now now this is a thing that happens to you when you're working on a robot. When you delete this, there is a final node that remains. Please don't forget to delete this, because otherwise you would have isolated nodes. So I'll basically delete this and delete the starter node. And where is the ender node? I cannot see it. I don't want to have isolated nodes, right? So let's open the node numbers. Yeah, there it is. Let's just hide this. There we go. You know what? I will keep it and show you a trick how you eliminate isolated nodes. I'll leave both of them. Okay? Let's open the section and let's remove the node points here. Notice you can detect an isolated node here, but you cannot detect this one here. So let's take a look later how we can fix that. But for now, let's continue. Now you notice that this one is a little bit too far away. This is solved in the site where artificially the beams section will extend, which means that this beam section becomes an L section. But actually, when we design it as a rectangular section. L section just adds a little bit of safety. And okay, so we have our first ribbed slab. Now we want to do our second ribbed slab. Now here's the thing. I want you to pay attention to practical reasons here. If you go and take a look on this, you see that in a panel, like let's take a look here. You can see a panel here, right? Let me just copy this and let's talk about this. Now you see that you can make out of some panels. You can make out of this panel, as you can see. You can make out of an adjacent panel, which is the red panel here, as you can see. And you notice something very important in those ribbed slabs. The continuity of a ribbed slab between a panel and the next panel is crucial, not only for practical reasons, but also for structural reasons, because the continuity of a rib causes the rib to be analyzed like a continuous beam, whereas if your rib is misaligned, then it becomes a simply supported, or not simply, I mean, it becomes a one-span rib rather than a continuous rib. So, for example, if you misalign those ribs, then this rib works independently of the rib beside it if it's misaligned. And you notice that in all ribbed slabs, the ribs are actually aligned, or we are trying to align them as much as possible for different plates. So let's take a look at the pictures. I mean, rib aligned, rib, here the rib is not aligned because it's perpendicular, but you can see here at least, let me show you the picture. You can see here at least that there are some tries to make the rib align with each other here so that the steel is continuous. And we're going to do that. So we're going to basically align the next ribs with those ribs. Now, do we have to draw new ribs? No, we don't need to draw new ribs. We can just extend this rib to the next span. So let's do that. Edit. I'll just say extend. And I'll select the boundary edge, which is this one. And then I'll extend the objects from the beginning. So let's do that. And now I'm extending. This is AutoCAD stuff. This is really cool. And this is why I love Robot. It just lends itself so well with the flow of work. Now notice I seem to mess up something. It seems that some of the rib is overextended. That's easy. I can trim them. So let's trim them. Also, I think there's a mistake here. Let me just check very quickly, because yeah, see, there are double nodes here. What I'm trying to say is I detected that a beam, or that I detected that one of those ribs seems to be going inside the column. So I thought that it's no way that it's going to be carried by the column. So remove the cross section. You can see the rib not being carried by the column. So it needs to be trimmed to the beam, because the beam is what carries this rib. Okay, speaking of trim, let's go to edit, trim. My trimming object is this, and let's start trimming. So let's trim this one. There we go. Perfect. And this one needs to be a little bit zoomed in, and we have it. Perfect. So now I have my perfect one-way structure, as it seems. Are we finished? No, of course. Now let's just do the isolated node very quickly. Let me show you how to detect and eliminate an isolated node. So if you basically run the analysis now, of course, I didn't do any loads, and the analysis is, of course, incomplete. But if you run the analysis now, you get an isolated node warning, which is kind of annoying because you don't see it. And this is the case because those two nodes are actually, in fact, isolated. Now, what's my trick here? I go to my node selector, hit all, and hit the Enter key. So it selects all nodes in the structure. As bold as it sounds, I hit the delete button. Now, Autodesk Robot immediately screams out at me, as it should be, and tells me that a lot of the nodes I selected are actually joining members. So what do you want to do? Do you want to delete the node and the member, or you only want to delete only the nodes that are not joined by the members? If you hit no, it will only delete the nodes that are not connected to any member. And you can see that now the problem of isolated node has been eliminated, because when you selected all and hit the delete button and ask it to no, not to delete the members, it only deleted the isolated nodes. If you run the analysis now, the isolated node problem has been overcome and you're perfectly fine. Okay, so are we finished? No, because we want here to have a two-way slab. So of course I need to add my second layer of ribs. So how do I do my second layer of ribs? I go to geometry. I basically first of all take this, and once again I will edit, move, or copy it. So edit, move, or copy. And the first one was, I forgot the number. So 0.385 in the X, nothing in the Y, nothing in the Z. I'll execute this, and now I have a offsetted beam. And now I'll transform this into a rib by magic. Oh wait, I messed up. I need to select the correct element. There we go. Now double checking everything by going to top maybe. You can see that perfectly aligns. Nice. Now there is a problem I will talk about later. You might even see this. If you see this now, you are a legend in my eyes. I hope that you see this. Tell me in the comment section if you already have seen it. Let me just edit, move or copy that thing. I'm gonna move or copy it by the spacing, the normal spacing, which is 0.52 in the X, nothing in the Y, nothing in the Z. And I'm gonna move it like, I don't know, for 10 times and delete whatever is not needed. So I'll execute this. We have copied that thing. And now I need to delete my members, which will cause all kinds of isolated nodes. I'll just delete this thing because I don't need it. And this is overshooting, so I don't need it. I'll delete that. And I'll delete the nodes here, basically, by hand. Because the Autodesk Robot will not detect this as isolated nodes. Because they are, in fact, not isolated. They are on a beam. Now, if you keep them, will this change anything in the analysis? The answer is no. Now, because I removed the cross sections, I actually have revealed my problem. The idea is that those elements should extend for the entire panel. This extension trimming happens whenever you have a panel that is not 90 degrees on each element. It's not like a perfect rectangle or square or whatever. Now I need to extend that thing. So okay, be my guest. Edit, extend. I select this to be my extension element. And let's extend those things, like one and so on. Wait, what? I didn't select it? Let's select that. And let's start extending. So there you go. And I think everything seems to be perfectly fine. Yeah. We are doing great now. Okay, so we have an initial structure now. Now we need to put a slab load basically on that thing. Now you have multiple options to do that. One of the options is just to put a cladding, a two-way cladding, and let robot deal with it. The second option is to put a slab of a very small thickness that just does not have any stiffness. I am not a fan of this. I'm a fan of basically putting a cladding. But the actual more accurate way is to put a thickness close to zero slab. So I'll just, although I'm a cladding fan, I'm just going to do this here. You can try do the cladding at home and tell me if there are differences. There will be differences, of course. I'll put me a 1 millimeter thickness slab. I will say here dummy slab. I'll add that. Of course, once again, I'm not doing any reduction of moment of inertia, but I've explained this before. I'll add that, close, and I'll just go full on contour. 1, 2, 3, 4, 5. I need to select this correctly. 6 and 7. And now I have a slab. I close that. Now, for dead load and live load calculations, I rely on you to be able to calculate your dead loads and live loads. For now, I'll just put me a 10 kilonewton placeholder load. I will talk about the calculation of loads maybe in a full video when I talk about the full structure. But for now, I'll just put me, I don't know, like 10 or 15 kilonewtons per meter square load just to take a look on the analysis of that thing. So I have it here on everything. I run the analysis, and spoiler, you will be unhappy with the results. So if you run the analysis now, wait, what? That seems to be strange. It did not do any finite element. Oh, I think I know why, right? Yeah, of course, curtain wall. I want a shell. For some reason, my Autodesk Robot, whenever I define a slab, goes to curtain wall, although it should be a shell. Your Autodesk Robot goes to shell by standard. I'm like surprised, to be honest. But let's run the analysis again. I should see a finite element mesh now. And there we go. I think it is working. Yeah, there we go. Now, of course, Autodesk Robot has an amazing mesher, but you can see some problems here. The problem here, why you see this nitty-gritty stuff happening, is because if you let's remove the mesh. Let's just remove the calculation. Remove the mesh to show you why this nitty-gritty stuff is happening here. Let's remove the mesh. Let me show you something. You see those 2 points are really, really close to each other, and that's why the finite element mesher is facing troubles here and facing troubles here. And that's why I told you, spoiler, you will not like the result. So let me show you again. You see, those 3 points seem to be a problem because they are having 2 elements intersecting near each other here. This element is intersecting, this element is intersecting, and robot fights for their life to mesh them. Similarly there. So how do we fix that? Now there is a practical fix, and I will do the practical fix basically. Of course, the theoretical fix is to forget about this and make the mesh size be 0.001 or something. But of course, this is like a nightmare for the finite element method. The practical fix is delete that thing. Let's just delete this and delete the adjoining element this time, yes. And now we are going to do it by hand. So I'll go here. The ripped slab is not easy to be modeled, to be honest, ladies and gentlemen. But well, I'm just going to do this now. So from here to here, trying to fix the problem. There we go. Now notice I am not being 100% accurate, but it's a good enough accuracy for me. So you could call foul and say, wait a minute, this is not parallel. Well, you are making blasphemy here. Yes, I am, but you have seen what happens with robot. This is numerical problems, so you could just use your engine. And that's why, ladies and gentlemen, that is why we need humans, and that's why Skynet, I'm winking to a subscriber here, that's why Skynet is not going to take us down anywhere soon. Because you need this human intuition. You need this human interference sometimes. So I'm just improving my model. I think I'm video editing this now. And now I have a somewhat accurate, like a highly accurate, by the way, model that should be easier for a robot to calculate. So let's run the analysis. I have an isolated node. Now I have still the fight here for dear life, yes. But it's much better than what was before. So I can still accept that somehow. Okay, why is this happening? Let me just quickly check. No, this is totally normal. I can accept that. But here I had a problem. Wait, what? Huh. Let me run the analysis again. Isolated node, right? Ah, you see? So, I think after the meshing video, you start appreciating those little tricks I have in my sleeve. You see, when I drew the new beam, it seems I messed up. Let me just delete that. Yeah, well, look, 23, 25, 27. Yeah, I totally messed up. This 858 was an incorrect node, so I'll have to delete that. For some reason, I have messed up my drawing, and I draw again. How do I know which one was the incorrect one? It was, look, 12, 13, 15, 17, 19, 21, 23, 58? No. So let's do it again. It's kind of annoying, but, well, it has to be done. Zooming, zooming, zooming. There we go. We have it now. Ah, see, it was snapping to this point. I don't know what this is. Oh, look, it was snapping to the parallel to 6. I don't want it. I didn't want it to be parallel to 6. Well, at least we have known now why the problem has happened. It's kind of, I don't know if it's kind of cool to see me mumbling around, but I'm just saying my thoughts here because it might be interesting. So, okay, everything seems to be fine. Now, this little thing is something we expect, and my initial coarse mesh seems to be working fine. So I'm happy now with this. So I'll go to my mesh basically here and just ask it to use fine. In my Autodesk Robot, it seems it's not working. And if it doesn't work, then I have to do it myself. Okay, now it works. Great. And you can see now the finite element mesh quality here is bad, to be honest, not that amazing. Okay, let me just do a check here. I'm referencing, what we do here is something you have seen before in the finite element meshing video. I just choose the basic precision here, select the panel here, apply. You see, you have some problems here. So what I'm saying here is that, well, in this region, the moments on the topping slab might be not really that great, but it's still reliable. Of course, if you go below 0.25, then okay, at least we don't have this. Now the scales, just check mesh quality metrics, and you see that 0.25 is bad. So at least we are in the good to okay-ish region. Now we have run the analysis, everything seems to be fine. Let's go to results and go to diagrams members, and you will not like this. Hit why? Oh, I am surprised. I am positively surprised. You see, I was spoiling and telling you will not like this because I thought that you will see so many squiggly things here, but you don't. What is happening here? And I said, I thought you will not like the result because I was banking on you seeing a lot of squiggly lines here, but you don't. Now allow me to explain to you what is happening here. So let me just select this bar, right click on it, and go to Object Properties, and basically throw it out as an NTM. If you click MY, you can see those squiggly lines. You can even go to Results, Detailed Analysis, and take it out for yourself to see. So MY apply, you can see there are some discontinuities here. There is some discontinuity here. And I thought those discontinuities would be bigger, and that's why I said spoiler, you will not like it, but in fact, I really like it. But still, the question remains, why do you have squiggly lines here? You have squiggly lines here because the ribs have torsional stiffness. And the torsional moment on the rib is going to be a bending moment uh, on the bar. I mean, let's take a look. Let me open a mix for you. You will see that the ribs, wait, I cannot see a mix. Why? Okay, no, not detailed. Yeah, this one. Let's open a mix here. Hit the apply button. And you can see there is some torsional moment here, 4.23. This 4.23 torsional moment should be the difference in the bending moment, to be honest. Let's just check this out. So to understand like the idea here is I want you to understand the relationship between torsion on one side and bending on the other side. So let's go to results, detailed analysis, and I'll open MY here for the beam here. Okay, wait, it's gonna be hard for me, right? So where am I now? Where am I? I am at, okay, the first, okay, it seems I'm here, right? All right, so let's go here. So I'm here basically. All right, so let's take a look. Now, just before the jump, the value was around 32.4, and after the jump, 36.7. It's not 4. Oh, yeah, it's 4. Wait, it's 4. So let's take a look. 32.5, 36.7, approximately. So 36.7 minus 32.5 is 4.2, approximation here, which is basically the moment you got here in the torsion. Yeah, perfect, amazing. I'm happy now. I'm really happy. I'm honestly happy now. I'm not just making this for the camera reaction. I'm really happy that it, whenever something like goes full circle, I feel happy and feel a sense of joy. Okay, so I'm removing the torsion, but you understand now that any squiggly things you see here is due to the torsion. Yeah, I think I've been video recording since 50 minutes, and I don't want to wing it because I want to talk about the design of those ribs in the next video. And those ribs need to be, you need to exercise care because those ribs do not carry any shear stirrups. And we need to find a way in Robot to do that. Otherwise, I would have to tell you that it doesn't work. So I will have to wait for it for the next week. But for now, I think I am happy. Not to be absolutely happy, I want to see the difference between the moment carried by the span that was one weight versus the span that was two weight. So let's select the rib. I selected the rib now, by the way. Let's go to analysis. Sorry, to results, detailed analysis, and let's take a look on MY for that thing. And yeah, I mean, yeah, obviously, you have. Let's take a look. This is 8. This is 8.32, I think, and this is 6.6. Yeah, you have a reduction moment, as it should be. The moment is not half to half, of course, but because there are stiffnesses involved. But at least there is a reduced moment here. That's nice. Okay. So I think I'm happy with this now. It's kind of cool. And please notice that analyzing a ribbed slab in a software is much, much more accurate than any approximate methods you were using in the university to approximate the load on the ribbed slab. Because here in a finite element software, you have much more accurate interactions because the interaction of the torsional moment of one element is going to be affecting the bending moment of the second element, and so on. Also, the stiffness, the torsional stiffness of the entire beam will affect the moment of the ribbed slab. So, I mean, if you want to do it, if you want to do a simplified analysis, you would basically WL square over 8 this thing, and try to find W, the load, by distributing the force somehow. Now, this is not 100% accurate, and allow me to show you what you are missing if you WL square over 8 that thing. If you WL square over 8 this rib and you are missing a negative moment due to the torsional moment of the carrying beam. This seems to be strange. Allow me to explain. If you go to results, diagrams from members, and select a mix, you can see there is a change in torsional moment in the main beam. And because there is a change in the torsional moment of the main beam, this change will be your bending moment on the rib. You don't believe me? Well, let's click it here. Okay, which one is this now? Okay, I need to find me a one that I can relate to. I'll select this one, this jump. This is node 40, right? If you stay here, let me show you. That's node 40. So basically node 40 is this one. There we go. And this is the place we want. Okay, fine. Now it makes sense to me. Now this is node 40, I think. Right? Yeah. This is node 40. And I want to see the jump in the moment here. So the moment here was 11.37. And then it's 14.2. So 11.37 minus 14.2 is around 2.8 moment. And this moment is the negative moment on the rib. So if you click on the rib here and basically take it, no, cancel, escape, take it and go to results, detailed analysis, again, and ask MY out of it, click OK. You can see at node 40 you have moments here. And the moment here, believe it or not, is 2.8 or something, the moment that it was the difference in the torsion. So what I'm trying to say is that no matter what you do in your approximate analysis, the finite element analysis will be a little bit more accurate because it takes into account effects that you are unable to solve by hand even with your approximate methods. So that's everything I wanted to talk about for this video, the first part of a two-parter of the modeling and design of ribbed slabs. The next video I'll be designing those ribs and talking about different aspects of the design and things you should take care of while you're doing that. And yeah, I will upload this model file and provide the link in the description of this video. And before I finish, of course, there is a deflection check for me. You get this deflection, which is 11.7 millimeters. This needs to be compared with your local codes. If it is good enough, fine. If it's not good enough, then of course you will have to increase the height of the rib, which means you would increase the thickness of your slab. And that's everything I wanted to talk about, basically. So in the end, of course, I hope that you enjoyed the video and that it was beneficial for you. If you have enjoyed the video, then please like, share, subscribe, and so on. Especially subscribing because it helps increase the reach of my channel. This is the Civil Engineering Essentials channel, and we'll catch you in the next video.